Roll number 1, Aditya Adok. Hello, Aditya Adok. Roll number 2, Archishna Adhikari. Am I audible?
Yes, sir.
Yes, sir.
Okay. Roll number 3, Abhonil Aich.
Present, sir.
Roll number 4, Deep Bagh. Deep. Roll number 5, Auro Bandopadhyay.
Present, sir.
Roll number 6, Somnath Bonik.
Present, sir.
Roll number 7, Rajdeep Bosu.
Present,
Rajdeep.
sir. Present, sir.
Roll number 8, Shreyoshi বিশ্বাস.
Present, sir.
Roll number 9, Sujata.
Present,
Nine.
sir.
10, Archishman Chakraborty.
Present, sir.
Roll number 11, Aditya Chakraborty. Aditya.
Sir. Present, sir.
12, Anjil Das.
Yes, sir. Yes.
13, Sringesh Das.
Present, sir. Present, sir.
14, Ayesh Dotto. Ayesh. 15, Mohana De.
Present, sir.
16, Shubhodeepa.
Present, sir.
17, Debnath.
Present, sir.
18, Ahana Dotto.
Present, sir.
19, Konishko. 19, Konishko Dotto.
Present, sir. Yes, sir. Present.
Okay. 20, Rana Ghoroi.
Present, sir.
21, Adrija.
Present, sir.
22, Ognibo. 23, Amritesh.
Present, sir.
24, Aditya Krishna.
Present, sir.
27, Pratikshita.
Sir, on
Present,
25.
Hello?
25 on Nash.
25, Ornes.
Present, sir.
26, Devdotto.
Present, sir.
Okay.
Present, sir.
27, Pratikshita.
Present, sir.
Okay. Sorry. 28, Shohom.
Present, sir. Present, sir.
29, Simoyi.
Present, sir.
30, Ayush Gupta. 30. 31, Dipon Hajra. Dipon.
Yes, sir. Yes, sir.
32, Shubhodeep Khan. 32, Shubhodeep.
Present, sir. Present, sir.
Okay, 33, Anushmita.
Present, sir.
34, Somojit Kundu.
Yes, sir.
35, Shovik Mal. Shovik.
Present, sir.
Okay. 36, Shubhodeep Manna.
Present, sir. Present, sir.
Okay. 37, Somokanto.
Yes, sir.
Mitra.
Yes, sir.
38, Shuggani Kumari.
Present, sir.
Right. 39, Ashmita.
Present, sir. Present, sir.
40, Obiraj Mukherjee.
Present, sir.
40.
Present, sir.
Okay. Then 41, Onesha.
Present, sir.
41.
Present,
Okay.
sir.
42. Shourab. 42 Shourab.
Present, sir. Present, sir.
Hmm. 43 Devjit. 43 Devjit.
Present, sir. Present, sir. Present, sir.
44 Tiasha. 44
Yes,
Tiasha.
sir.
Hmm.
Yes, sir.
Okay. 45 Rajibul. 45 Rajibul.
Present, sir. Present, sir.
Okay. 46 Sounok Roy. 46.
Present, sir.
Hmm. 47 Shoham Shaha.
Present,
47.
sir.
Okay. 48 Shumi Shaha. Shumi
Present,
Shaha.
sir.
Hmm.
Present, sir.
Okay. 49 Shubhonita.
Present, sir.
Shubhonita, why?
Present, sir.
Okay, it's all right. But you should be careful, Shubhonita, when you are writing your roll number. In earlier assignment, you have written roll number 48. Okay.
Sorry, sir.
Mm-hmm. Roll number 50. Roll number 51. Roll number
Yes,
51.
sir. Yes, sir.
52 Rupok.
Present, sir.
53 Akanksha. 53 Akanksha. 53 Akanksha.
Present, sir. Present, sir.
Okay.
Present,
Uh,
sir.
okay. 54 Shruti Kumari. Shruti
Present, sir.
Kumari.
Present, sir.
Okay. 55 Shomika.
Yes, sir.
Okay. 56 Unkita.
Present, sir.
Okay. 57 Himatri. Himatri.
Present, sir. Present, sir.
Okay. 58 Tipu Sultan. 58 Tipu Sultan. 59 Aditya.
Present, sir.
Okay. So what last time actually, at what point we left under atomic and molecular structure, in case of crystal field theory, we tried to explain actually the under various conditions that what kind of octahedral crystal field splitting we observed and the tetrahedral, etc. by taking so many examples. The high spin complex, low spin complex, the how we can calculate the crystal field stabilization energy, and then the pairing energy, and altogether the total stabilization energy. When does it happen? Under which condition? But once again, I would like to remind you that as far as the crystal field splitting is concerned, it is nothing but simply it is a breaking of degeneracy of d atomic orbital in the spherical field because of the influencing ligands when they are going to form the coordinate bonding or complexes. Basically, it is the concept based on either that electrostatic force of attraction, there will be at the same time simultaneously electrostatic electronic repulsion between the ligands as well as the d atomic orbital electrons of the central metal atom, and due to that there will be the breaking of degeneracy of d atomic orbital. That is the concept of crystal field splitting. In the process, with respect to the approaching ligands along the direction of x, y, z, or in the direction between x, y, x, y, y, z, and x, z, you understand the crystal field splitting is going to be what is going to be the nature of the crystal field splitting in case of the octahedral complexes. It is going to be just opposite in case of the tetrahedral field tetrahedral field complexes. The why? Because whenever the breaking of degeneracy of d atomic orbital is taking place into two set of atomic orbitals, one is triply degenerate dxy, dxz, dyz, and another is dx square minus y square and dz square in case of the octahedral complexes. As with respect to the approaching ligands, with respect to the geometry, you can find in along the x, y, and z direction, the repulsion is going to be very high. So therefore, the energy level of dx square minus y square dz square, that is actually E to G is going to be at higher level. On the other hand, the triply degenerate, that is actually you are finding a DXY, DXZ, DYZ compatibility is going to have lower electronic repulsion, so therefore it is going to be at lower energy level. On the other hand, as far as the tetrahedral field is concerned, you are finding that here the approach with respect to approaching ligand, the XY and the XZ and YZ, there will be more higher electronic repulsion. So that's why here rather T2 it is going to the higher energy level, and whereas E is going to be the lower energy level. That is dx square minus y square and dz square in case of the tetrahedral complexes. Okay. And at the same time, you understand that due to the number of ligands in case of the octahedral field complexes, in comparison with the tetrahedral field complexes, generally splitting is going to be higher. So therefore, del O, that is for octahedral crystal splitting, is greater than del T, the crystal field splitting for tetrahedral complexes. And up to what extent, normally you can expect the del T nearly equal to 4/9 del O. Okay, also. So that you already know it very well. Now let us understand today actually in terms of how we find the different types of color actually in case of the complex ion, because with respect to the paramagnetism and the pairing energy, etc., we have already explained it. Okay, so let us share this. Just a minute.
Sir.
Yes.
Sir, when will be our internal examinations and second internal examinations?
Everything you will come to know actually. Just by this week you will be able to know that when it is going to take place. Okay.
Okay, sir.
Will it take this week only?
Will it take this week only? Yes, most probably.
I mean that the exam will happen on this week only.
Most probably. As far as I know, most probably it is going to happen like that. Okay.
And the syllabus?
Just a minute, okay. Hello, am I audible?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay, just a minute. Everything I will let you know. Don't worry about all this. Whatever we are studying, naturally the syllabus is not going to be out of that. Means syllabus is not means it is going to be including that actually. Okay. So nothing. Don't have to worry about that. So now I'm going to share the screen. Just a minute. Hello, what's the screen is visible right now?
No, sir, it is not visible.
Not
Yes, sir.
visible.
Coordination.
Coordination chemistry.
It is visible, sir.
Coordination chemistry is visible. Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine then. So coordination chemistry, isn't it? It is visible. Okay?
Yes, sir.
Okay, very good. Just a minute. All these actually we had explained earlier. And as we are explaining this, we have come to this point, how we can explain the various types of color, complex salts of soap. And let us continue from that. So all these we had explained earlier also. So nothing new, you understand. Now colors of transition metal complexes, whether is it visible? Hello?
Yes, sir.
At present, we have focused on mostly the octahedral complexes. So you understand that compounds and complexes that have colors, so naturally it should be in the visible range actually, visible light range that absorb specific wavelength, that is 400 to 700 nanometer, or you can say 4000 to 7000 angstrom. Okay, and here you can find generally we can observe the color of the transition metal complexes in terms of the photon if it is in this wavelength or specific wavelength or so. Okay. Now, in this context, I would like to tell you, normally, as such, any substance, it cannot have direct any color or so. Actually, what we are observing, that is going to be color. Okay. Then how it is happening? Normally, whenever you can find any substance is white, you are finding, that means colorless, or rather you are saying white, then it is understandable that whatever the photon actually incident upon it, that object is going to reflect all of this light actually, and naturally it is not going to absorb, and that's why we find it is white. On the other hand, in general, whenever we are finding any object is black, so that means it is understandable that whatever the light incident upon it, it is going to absorb all these wavelengths actually, because you know that the white light is basically polychromatic in nature of different types of wavelengths, the 7 Vibgyor in color, as you understand very well. So that object is going to absorb, and actually it is going to that's why we see it actually black, because nothing reflect of any remaining wavelength of that photon. Okay, what is being incident upon that object. On the other hand, whenever we are seeing any object is color, basically what we find that the some part of that white light of specific wavelength of color is being absorbed, and what is not being absorbed actually, that actually transmitted through, and that we are seeing actually. Okay, and here we can find the complementary color. In that way we can find that what should be the specific color of that object, and let us understand one by one. For example, look at here. The visible spectrum we have shown, that is the Vibgyor, violet, indigo, blue, green, yellow, or orange, or red. Generally, you can find some colors are very much overlapping. So naturally, we will consider violet, blue, green, yellow, orange, or red. And if I understand that from left hand side to right hand side in this screen, 400 nanometer to 700 nanometer. So that means the wavelength increases. Okay, and you know the 400, that is the violet, and 700 suppose red, and you know the beyond 700, that is invisible, that is the infrared, and the beyond 400, that is the ultraviolet, that is also invisible. You know, and you find from left to right here. Basically, the energy increases, so that means E is equal to h nu. So energy is directly proportional to frequency, and whereas you can find directly proportional to wave number also. Okay, and whereas it is inversely proportional to wavelength. So therefore you will find the rate energy of longer wavelength among this Vibgyor, and whereas the violet is going to be the shortest wavelength, okay, of this color range. Is it clear? Because of its higher energy. Hello, up to this it is understandable?
Yes, sir.
Okay, fine. Now, if you share the next slide, look at here. What is happening? For example, the Newton's color disk from here, we understand that this is the complementary color. Suppose if red light is absorbed by any object, we will see what's the transmitted light, green in color. And suppose the vice versa, if the green light is being absorbed by the same object, object, then we will see the red color is transmitted like that. Similarly, you will find the complementary color. Suppose if orange color is absorbed, then we will find the observed color is blue. So the vice versa. So orange and blue, then you are finding yellow and violet, and red and green. This is understandable what I am saying?
Yes, sir.
Okay, very good, very good. Then, if we share the next slide, if you look at this, the colors of the transition metal complexes. For example, the white light is passing through that, or the white light is actually being incident upon that object. Okay, and now because of electrons actually, it is absorbing the energy, it may jump. For example, I am saying in case of the octahedral complexes, the from triply degenerate to doubly degenerate, there will be the jumping of the electron. Okay, and in between, the crystal field splitting energy is already there. So here, the higher the crystal field splitting, the higher the energy is required by the electron to jump into the doubly degenerate dx square minus y square and dz square level. Okay, and that is possible when you are considering suppose the dd electron transition. So now look at here. Suppose the white light is incident upon that substance, and here you find the red light is being absorbed. So that naturally we are getting, and because of the red light absorption, you are finding one electron jump from the lower energy to higher energy level. For example, I'm saying, okay, this one actually it should be in the higher energy level, and therefore you are finding actually the complementary light, that is the green light, observed. So therefore it is understandable that for transition metal complexes, the octahedral splitting, for example, in this case we are considering, similarly in case of a tetrahedral also you will find, flat planar you will also find, that is different thing. But suppose crystal field splitting actually correspond to the energy of the visible light, and absorption raises an electron from the lower d subcell to the higher d subcell. So that's why we find the color of the transition metal complexes. That means for transition metal complexes, what's the energy splitting actually in terms of that energy difference between the triply degenerate at the lower level and the doubly degenerate at the upper level for octahedral complexes, suppose as we are explaining right now, correspond to the energy of the visible light, then the absorption rises an electron from the lower d subcell to the higher d subcell. Okay, this is up to this, it is understandable up to this. Any doubt, you don't hesitate to ask me. Now, as we find, the different complexes exhibit different colors, because color of the light, because color of the light actually depends upon the energy difference. Larger the energy difference means larger the crystal field splitting. So naturally, for any electron to jump from lower level, triply degenerate to doubly degenerate in case of the octahedral, and in case of the tetrahedral it is vice versa, the higher energy light absorb. The higher energy light absorb means shorter wavelength. And whereas if the crystal field splitting is small, then the smaller energy is required. So that means lower energy light absorb. That means of longer wavelength. So therefore, this magnitude, the del depends upon several factors, as we explained in case of the crystal field stabilization energy. Now here you find at least first in terms of the ligand, whether it's a strong field ligand, whether it's a weak field ligand, then the metal atom, the type of metal atom, what are the d electronic configuration, then this oxidation state like that also. Okay. Hello.
Yes, sir.
Okay,
Yes,
fine.
sir.
Okay. Now you just see this is you are finding that the chelate complexes coordination number is 6 and the oxidation state of Mn is actually 3+. Here you are finding it is ethylene diamine actually, or you can say it is ethane 1,2 actually diamine, and the metal oxidation set T ion also. Okay, these are hexadentate ligand, and means you are finding the bidentate ligand. It is forming actually 6 coordination number octahedral complex, and here you are finding it's forming the chelate complex. Suppose the white light is passing through these complexes, okay, and a blue light is absorbed, generally En, nearly to the near to the strong field ligand in the petrochemical series. So it is causing actually high splitting. So naturally the blue light absorbed, that means higher energy light, okay, from jumping from the lower level to higher level in terms of the, as you sometimes say, the DD electronic transition. And then what we are observing, when blue light is being absorbed by that substance, we are observing the complementary color, that is the orange light. Because if you remember, I had shown you earlier this one. Look at here. That for blue and orange, they are complementary lights of each other, complementary color of each other. Hello? Understandable?
Yes, sir.
Yes, sir.
Okay, fine.
Yes, sir.
Then if you take this example, what you are finding? That you are finding the hexafluoridochromium 3 ion. Okay, then you are finding hexa aqua chromium 3 ion. Then you are finding hexa amine chromium 3 ion. Okay, and here, okay, then the first case actually you are finding rather hello. Actually, you are finding the hexa fluorido because this is the anion, so chromate actually. And the last one you are finding that hexacyanido chromate 3 ion. Is it clear?
Yes, sir.
Okay, very
Yes,
good.
sir.
Okay, very good. Now, in this case, you are finding in all these cases, what you observe, the oxidation state of chromium is +3. And whereas as well as you are finding coordination number is 6. So in all these cases you are there showing the octahedral geometry. Okay, now if you look at the nature of the or type of ligand, you are finding these are actually different. If you look at the spectrochemical series, then you will observe that from weak field to strong field ligand, you are finding from fluoride to aqua, from aqua to ammonia, and from ammonia to cyanide. That means from weak to strong field ligand. Now look at here. If you see the splitting, so as you find the fluoride, that is actually basically you are finding it is a weak field ligand. So you just see the splitting, the breaking of the degeneracy is less between the triplet degenerate and the doublet degenerate. And as you are finding oxidation state is +3, so naturally you are finding by Hund's multiplicity the dxy 1 electron, actually T2G3 and EG0. Okay, the first thing. And then you are finding that here as far as T2G is concerned, you are finding dxy1, dxz1 and dyz1 in all these cases. But if you look at the del O, that means the crystal field stabilization energy between these two set of degenerate atomic orbital, then you are finding from left hand side to right hand side gradually the del O is increasing. Why? Because every other things are common, but one thing is uncommon. In terms of the ligand, from weak field ligand to strong field ligand, from the spectrochemical series, from left to right, it is increasing. So that's why crystal field splitting is increasing. And due to that, here if you see the what's this complex ion, where you are finding hexafluorido chromate 3 ion, what you are finding the color green. The here you are finding the CrCN6, that means hexacyanido. You are finding chromate, that is actually you are finding the yellow color. Okay, why it is so? Because if you look at this, that here the low energy it is required. Suppose in terms of, for example, it may be in the red in color also. Okay, the wavelength, because here it is the lower energy splitting. That's why you are finding the color is just opposite green. And whereas as you are finding the Cn minus being a strong ligand, the crystal field splitting is very high, and that's why it requires actually energy of actually shorter wavelength. And from that point of view, if you look at this, the color ring, then you can find the for yellow that you are finding in the visible range color the opposite violet of the shortest wavelength. So that's why you are finding here, as far as the complementary color, that means what is being transmitted, what is not being absorbed. For example, here in case of this CrCN whole 6,3 minus, you are finding yellow color, and whereas CrF6,3 minus, you are finding green. So that's why you are finding like this the nature of the color of the different type of complex salt or complex ion. Is it clear? Any doubt? Hello?
Yes, sir.
Okay, further I'm explaining. Just a minute. Further I'm explaining. Okay. I'm taking another, and then you will be able to understand. Look at here. You just see color of transition metal complexes. The variety of color among transition metal complexes has long fascinated the chemistry. For example, aqueous solution, you see the hexa aqua iron 3 ion are red. You already know very much that in case of the ferric, generally yellow to red is actually color. And then you can find, that's why you say the ferric hydroxide by ferric oxide, that is red is brown in color. Then you are finding hexa aqua cobalt 2 ion are pink. Then you are finding that hexa aqua nickel ion, nickel 2 ion are green, and whereas you are finding hexa aqua cobalt 2 plus. I mean, hexa aqua cobalt actually you are saying 2 ion. When 2 means oxidation state are actually pink, and you are finding means are blue, and whereas you are finding the zinc hexa aqua zinc actually 2 are colorless. Though you will see that COH2O whole 6 2 plus, it is actually octahedral are pink, and those of tetrahedral COCl4 2 minus are blue. And the green color of hexaquar, this turns blue when its ammonia is added to give this. So many of these facts can be actually explained by crystal field theory. How we can explain it? Try to understand first of all. Hello, this kid is visible. Hello.
Yes, sir.
Yes, sir.
Okay. Okay, fine. First of all, I would explain that ZnH2O whole 6 2 plus. Naturally, it should be colorless. Why? Because Zn2 plus means you are finding it is 3d10. So that means here whether all the d atomic orbitals in the triply degenerate state or the doubly degenerate state are paired. So naturally, there are no question of in this case the dd condition. And not only that, you are finding that the H2O is also at the same time the weak ligand. So here charge ligand transfer is also not taking place. So that's why it is going to be colorless. Okay. But the moment you are coming to the hexa FeH2O 6 3 plus are red in color, and COH2O 6 whole 2 plus are pink color, and NiH2O whole 6 2 plus are green color, CuH2O whole 6 2 plus are blue color. So this is because of the DD transition. That means it is generally takes place from the triply degenerate to doubly degenerate also. Okay. And whereas you are finding that in case of the cobalt H2O6 2 plus are pink in color, and for tetrahedral are blue in color. Because as you understand that in case of COCl4 2 minus, so that means in this case also oxidation state of cobalt plus 2, no doubt. And in case of COH2 whole 6 2 plus, here also you are finding 2 plus oxidation state. But why it is pink in case of the octahedral, and why you are finding tetrahedral are blue? It is obvious because in terms of the crystal field splitting, first of all, you know that in case of the tetrahedral, they are lower splitting actually. The del T is less than del O, first of all. And secondly, also you know, because the number of ligands Cl minus is less than that of H2O in comparison with the cobalt. And at the same time, again, you understand that the Cl minus is further weaker ligand than the H2O. So naturally, you find the what will be the transmitted light in terms of the complementary color. You will find mostly the hexaqua cobalt, that is octahedral complex, you are finding a pink, or whether those of tetrahedral you are finding a blue. On the other hand, if you consider the green color of NiH2 whole 6 2 plus turns blue when ammonia is added to give NiNH3 whole 6 2 plus. Why? The reason is that you understand that when in case of the hexaqua nickel actually, so what's the H2O and ligand, and in case of the NiNH3 whole 6, here also Ni2 plus, same metal atom, same oxidation state, but in case of the ammonia, it is going to be comparatively strong ligand than that of the H2O. So that's why you are finding the what will be the color of the nickel H2 in terms of the crystal field splitting. And in case of the nickel NH3 plus, you are finding the crystal field splitting is going to be more. Okay, and therefore you are finding here in this case Actually, ammonia and water, though some extent, nearly you can say, but still ammonia is slightly higher. And here, that's why you are finding that the hexaqua nickel turns blue, and when ammonia is added to give that hexaammonia nickel ion, it is going to be actually you are finding turns blue actually from green to blue also, like that. So now, as we have already explained, the why we see color, whether this screen is visible. Am I
Yes.
audible? Whether it is visible? Any
Yes.
question you can ask me in between.
Yes,
Yes, sir.
sir.
Okay. Now you see the what we have already explained. That when a sample absorbs light, what we see is the sum of the remaining colors that strikes our eyes. And if a sample absorbs all wavelength of visible light, none reaches our eyes from that sample, and then the sample appears black. Already you know. And if the sample absorbs no visible light, it is white or colorless. So therefore, when the sample absorbs a photon of visible light, it is its complementary color we actually see. For example, if the sample absorbs orange color, it would appear blue, and blue and orange are said to be complementary color. Look at here, the color wheel. Red complementary green, okay, violet complementary yellow, and vice versa, and the orange complementary blue, and vice versa. So therefore, look at here, the color of light absorbed on the left hand side, and what's the wavelength range you are finding. Look at here, that from 700 starting, you are coming up to nearly 400 nanometer from top to bottom. In this different range, you are finding, suppose red color is absorbed, you are finding complementary color green, you are actually seeing visible. Similarly, orange color is absorbed, blue, yellow color is absorbed, violet you are seeing the complementary color. If green is being absorbed, the red, the blue is absorbed, you are finding orange, and violet is absorbed, you are seeing the yellow color, like that. Okay. And here, as I have already explained, you already know the color of the coordination complexes. The color of the coordination complexes arises from electronic transition between levels whose spacing correspond to the wavelength available in the visible light. In complexes, these transitions are frequently referred to as DD transition, because they involve the orbital that are mainly D in character. For example, T2G and EG for the octahedral complexes, and E and T2 for tetrahedral complexes. That means for octahedral complexes, T2G at the lower energy level and EG are the higher energy level. And whereas for tetrahedral complexes, you are finding E at the lower energy level and T2 at the higher energy level. Obviously, the colors actually exhibited are intimately related to the magnitude of the spacing between this level, as we have already explained. And since this crystal field splitting actually depends on factors such as geometry of the complex, it is very much, as you know, the nature of the ligand and the oxidation state of the central metal atom. As you know, the variation on the color can be explained. Okay, what we have already explained. And look at here. Here, oxidation state, suppose VH2O6. Okay, V is suppose metal atom. VH2O6, V is the metal atom. Now, here you are finding the oxidation state of this metal atom is actually 3 plus on the left hand side, and the right hand side you are finding 2 plus. So therefore, on the left hand side you are finding D2 ion, on the right hand side it is D3 ion. And look at here. Already, if you remember, we said that for the same metal atom with the higher oxidation state, the crystal field splitting is going to be higher. So that's why on the left hand side, when the oxidation state is +3 and it is having D2 electron, you just see the octahedral splitting is very high. In comparison, on the right hand side, if you look at the crystal field splitting, then here you find that because of lower oxidation state, it is less and it is having D3 ion. Okay, and here you are finding it is less. So that's why in the left hand side you are finding violet light absorbed complex appears yellow for the same central metal atom. Okay, with the same ligand, same geometry, only the variation is the oxidation state. And on the other hand, on the right hand side you are finding the yellow light absorbed complex appears violet, because the left hand side del is large, del O is large, whereas on the right hand side del O is less. Whether it is understandable? Hello?
Yes, sir.
It is clear,
Yes,
no?
sir.
Good. So that's why you are finding like this. Now again, Let us take this example. Suppose you are finding that is the homoleptic complex ion CrNH3 whole 6 3 plus. Okay, and the next one you are finding heteroleptic actually complexes that you are finding heteroleptic because they are not the same kind of ligand. Here you are finding 5 amine ligands and ammonia ligands, and another is the chloride. However, if you look at the oxidation state, in both the case, you are finding chromium is +3 because here in the first case 3 plus because you know the ammonia is a monodentate ligand, and in the second case you are finding the chloride is monodentate but negatively charged. So that's why you are finding the chromium. Overall, the complex ion is 2 plus charge, but chromium is 3 plus oxidation state. Now, what you are observing? Here you are finding all the ligands are same, and here you are finding in place of one of the strong ligand, suppose one of the ligand ammonia, which is comparatively stronger, is being replaced by chloride ion. So that's why here you are finding the left hand side in case of hexaamine chromium 3 ion, and here you are finding actually the pentaamine chlorido chromium 3 ion. You are finding the weak splitting. So that's why the low energy yellow light absorbed on the right hand side and the complex little bit magenta in color. Okay, and whereas on the left hand side you are finding the high energy violet light absorbed. So that's why complex you are finding yellow in color also. Hello, am I audible? It is understandable?
Yes.
Yes, sir.
Okay, good. So these the variation in the color of the chromium 3 complexes already I have explained. Okay. Some sound is coming. How it is coming? And look at here. If you remember in our actually first internal, I said one question actually. Suppose titanium hexaqua titanium 3 ion, for example. Okay, if it is perfectly octahedral, should give only one DD transition. Why? Because in case of the titanium, you are finding the electronic configuration is D1. So naturally, you can expect that that one electron should jump to the higher energy level. Okay, from triply degenerate to W degenerate. However, distortion occurs to eliminate the degeneracy of the system. Why? Because whenever you are writing the electronic configuration, for example, I'm saying that you will come to that later on, the John Taylor distortion actually, which you will observe mostly in case of the D9 complexes. Okay, so long it is D1, D2, that is also observable, means distortion, but normally in case of the DXY, DXZ, DYZ, as they are not directly directed to the approaching ligands actually. So that's why here that sort of electronic repulsion is less, though maybe due to the presence of 2 electrons in the triply degenerate actually DXY and DXZ, suppose D2, 1 each, and the DXY only 1. In that case, some distortion it may happen, but it is not so significant. Rather, in case of the octahedral complexes, we will find that when it is suppose the D4 with high spin complex, and as well as in case of the D9 configuration, where we may observe the John Taylor distortion, because generally we observe in case of more directly XY, x square minus y square, and z square ligands actually with a direct approach. In case of the octahedral complexes actually become asymmetric. In case of D4 means a high spin, that means when the one electron goes to either dx square minus y square or dz square. And in case of the D9, as you find that the triply degenerate actually all fill up, and with the in case of the doubly degenerate, that the E to G, there will be one electron actually there in one of the atomic orbital. In other, you will find suppose 2. So naturally there will be asymmetric. So in that case, we may observe. That I will come to this later on when we will try to explain the John Taylor distortion. So here you look at this, should give only one DD transition, that is expected, perfectly octahedral. But however, if you look at this actually, what is the absorbance actually, we observe that it is in the normal like octahedral splitting is not happening. you are finding further more repulsion. Actually, you are finding dxy, it is coming below the dxz and dyz, and whereas dz square, it is going, that means along the z axis, it is going to have little bit higher distortion. Somewhat you can say, for example, the z out also, like that. So therefore here you are finding, if a complex distorts from regular octahedral geometry, the T2G and EG levels are split, and the consequence of which the appearance of a shoulder as shown in the figure right. Okay, you are finding like this. And whereas, as you understand, the complexes that contain metal ions of D10 electronic configuration, you can expect the colorless because all the electrons are paired. So there is no possibility of DD transition. Okay. One would expect a metal complex with no d electron to be colorless. The other day we might have explained such cases. Suppose the manganate ion, that is suppose for dichromate ion. Suppose the chromate ion. Here you are finding Mn plus 7. Okay, so Mn plus 7, no electron in the d atomic orbital, d0, and in this case Cr6 plus. In case of the dichromate, d0. In case of CrO4 2 minus, the chromate, you know, that is also you are finding the actually. Hello, are you getting my point?
Yes, sir.
Yes, sir.
Yes, sir.
In that case also chromium plus 6. So naturally you are finding that also there will be no d electrons. Then how it is possible? So the origin of this color in this complex is not the d transition, rather due to charge transfer. That means actually ligand charge transfer to the metal ion. Why? Because metal ion is having the vacant d atomic orbital. So naturally the negatively charged ligand, it will be attracted more by the central metal ion, and because of that the electric charge transfer from ligand and to this central metal ion, and this charge transfer actually in terms of energy transmission involvement in so high in comparison with the DD transition. So that's why you can find that in case of the manganate, potassium dichromate, potassium chromate, so bright in color, so dark type color also. Okay, highly. And in case of the multi-electron system, exhibit multiple transition, and you understand the absorption bands actually are not so simple, not straightforward. So many factors come into play. So the complexity arises due to always, definitely you will understand that in any type of in chemical compound behavior, their chemical properties, etc. You will find the somewhat, mostly you will find inter-electronic repulsion. Inter-electronic repulsion, the very important things, and how and this actually comes into play to decide the so many factors or so many properties generally are being exhibited by a given chemical substance also. So therefore the complexity arises due to inter-electron repulsion. Okay, and that is beyond our scope in terms of discussion. Now let us understand to understand more in the simple manner the color of the coordination complex as we have explained like this. That you will study under spectrochemical, that the selection rules for the electronic transition. A means absorption, log base 10 I0 by I equal to epsilon Cl, where epsilon is the molar extinction coefficient, A is the absorbance, and C is the concentration of the sample of which you are finding by Lambert-Beard law, mole per liter, and L is the actually that is your polarimeter tube. L is the path length in the centimeter, and A is known as absorption, and it is dimensionless. Okay, so these actually it is under there in the under spectroscopy also. So here, suppose they have applied some rule actually. The octahedral complex, suppose as we explained that it is having some symmetrical, centrosymmetric at the very beginning under Christoffel theory, and whereas tetrahedral you have found that is the non-centrosymmetric also. Okay, and you know that in case of the tetrahedral is a epsilon, you are finding is 100 times greater than the epsilon OH, means for tetrahedral octahedral. That's why you find the hexa aqua copper, which is a rather pale blue color, versus tetra amine copper actually, which is an intense dark blue. In fact, basically, you will find like this intense dark blue color. Okay, that might be the reason. Why? The unsymmetrical vibration of an octahedral complex can transiently destroy its center of symmetry and allow transition that would otherwise be Laporte forbidden. In case where the rule applies, the color of the complexes are usually relatively pale, and so therefore, which is a rather pale blue color that we are not going to explain right now. Then what I tried to explain, the charge transfer bands. Similar to DD transition, charge transfer actually transition also involve the metal d orbital. Okay, so here charge transfer bands are observed if the energy of the empty and filled ligand. For example, I'm telling what's the example I've taken for manganate ion, dichromate ion, in case of chromate ion. Here you are finding the in case of the everywhere you are finding in this tree the ligand is O2 minus. And whereas you are finding Mn7 plus, Mn6 plus are being actually D0. So therefore here the charge transfer takes place here between actually ligand to metal ion. On the other hand, it is also possible metal to ligand, that is the where the pi bonding is there actually. The suppose in case of the carbonyl group present, for example, cyanide also it may be present. But most you observe in case of the carbonyl group containing compound. Suppose you are finding neutral complexes like the NiCO whole 4, then FeCO whole 5. So in this case, here you may observe the charge transfer rather from metal because here oxidation state for Fe. In case of FeCO whole 5, in case of the NiCO whole 4, the oxidation state of the nickel is all these cases 0. Okay. And here you are finding the charge transfer generally takes place from a central metal atom to actually the ligand, because the carbonyl group that it is having the pi bonded electron cloud, some incompleteness. So here you find the ligand charge transfer. Okay, suppose APBPY means bipyramidal actually. Means by pyridine, so there are two pyridine molecules are connected, so that's why in this complex the charge transfer occurs from Fe2 to empty pi orbitals of this BPY ligand, and that means you will find that in case of FeCO whole 5, then if NiCO whole 4, here you will find the charge transfer even from the neutral central metal ion to the empty pi orbital of carbonyl ligand. Okay, and look at here the color of the KMNO4. Here you are finding that ligand and the metal ion charge transfer, and whereas what I have explained right now, that metal to ligand charge transfer, you are finding the transfer of electron from metal's d orbital to pi bonding orbital of carbonyl ligand. Suppose in case of the FeCO whole 5, in case of the NiCO whole 4. Okay, so favor electron rich metal center and those ligand by pi acceptor. Okay, so here you find the movement of the electron between metal and ligand often 1000 times stronger than the normal DD transition band. Hello, understandable what I am saying, what I am explaining? Hello, it is becoming one-way traffic. Am I audible?
Yes, sir.
Yes, sir.
Okay, so therefore you understand that in these cases, whenever you are finding the charge transfer, whether it is from ligand to the central metal ion and whether it is from metal to ligand, when under which condition it is happening, you might have seen here, and there you are finding that these metal ligand charge transfer, or the rather movement of the electron between metal and ligand, you are finding often 1000 times stronger than DD transition band. And when we observe, look at here, under LMCT, the transfer of an electron from p orbital on a chloride, suppose, to a metal's d orbital, it is possible. Similarly, you are finding favorable when metal center is in a high oxidation state. So when it is in higher oxidation state means when you are finding there will be more and more, means less and less d electrons, means more and more vacancy of the d atomic orbital. And here you will find the common for pi donor ligands like F minus, O2 minus, N3 minus, OH minus. For example, what we have explained, the color of KMNO4, D0 complex. Okay, and whereas when you are finding the metal to ligand, just opposite, metal to ligand charge transfer. You are finding transfer of the electron from metal d orbital to pi, suppose pi antibonding orbital of carbonyl group. Because you know the C triple bond O, okay, empty pi orbital means antibonding here you are finding. Okay, and here what you are finding, basically when the oxidation state of the central metal atom is very less. For example, as I am taking example repeatedly, in case of the ApCO5, NiCO5, they are normal zero oxidation state. So naturally, from the d atomic electrons or electron from d atomic orbital to the antibonding pi orbital of the carbonyl ligand, it is shifting and favor electron rich metal center. As that's why I'm saying the favor electron rich metal center, and those liganted by pi acceptor and often higher in energy in the UV region. That means it is a very higher in energy, UV region, ultraviolet region. Okay, so ultraviolet region means you would not be able to visible actually. That's why you are finding the charge transfer fully allowed. For example, MnO4 2 minus once again. Okay, and you find suppose KMnO4, actually here it should be MnO4 minus 1 actually. Okay, you just see, look at here, almost 1000 times more than the spin forbidden DD transition also. Okay, an example you just see the MnH2O whole 6,2 plus high spin D5. Then you are finding centrosymmetric complexes, suppose hexa-aqua titanium 3 and D1 example. And whereas charge transfer fully allowed MnO4 to minus, MnO4 minus, clear? And whereas NiCl4 2 minus, you are finding this type of epsilon absorbance. Hello, up to this it is clear, understandable?
Yes, sir.
Hello? Okay.
Yes, sir.
Then the next class, we will explain the John Taylor distortion, okay, then to some extent the square planar splitting in terms of that for other than octahedral and tetrahedral, and also in the same line, because you are having the separate chapter under actually stereochemistry of the organic compound rather, but stereochemistry that also cover other than organic compound, inorganic compounds, because in continuation of the coordination compound like transition metal complexes, we will also try to explain to some extent its stereoisomerism, because you know the stereoisomerism that is under two broad classification. One is configurational and another is conformational. Under configurational, you know it very well. So one is geometrical, the other one is optical. So naturally, in continuation, we will complete that portion under this atomic and molecular structure, and then we will complete the band theory very quickly within coming 2 days. And after that, we will start a new chapter separately, that is actually stereochemistry. And already before that, we will explain under this topic in continuation of coordination compounds under crystal field theory also. Okay. Hello.
Okay, sir. Okay.
Yes, sir.
Any question? Any more? Hello.
Sir. Sir. Sir, what are the chapters that we will have in our internals?
I will let you know.